In the last video we discussed the work done by a force on an object as an object moves over a straight line distance, and we considered only the cases where F is a constant force. In this video we will look at the idea of the power of a force F on an object. This is the rate of work done by the force F on the object. So the rate is the amount of work done every unit time. Well, the unit time that we will use is the second. Now, here is an example that we saw in the previous video. To get the work done by this force, we get the component of this force in the direction of motion. So we are assuming that the object starts here and moves in a straight line motion over to this position. It moves a distance of 20 meters. Okay, so we just multiply that component times the distance. So the component of this force in the direction of motion is equal to the force itself actually, because it's pointing in the direction of motion. The distance is 20 meters. So that's the work done by the force. Now let's suppose that it took, say, 10 seconds for the object to go from here to here. So at t equals 0 the object is here, and at t equals 10 the object is over here. Constant force of 100 newtons to the right acted on the object. So we can get what's called the average power of this force F on the object. We just divide the work done by the force on the object by the time taken for the object to go from here to here. So the work done is 2000, the time is 10, so 2000 joules divided by 10 seconds is 200 joules per second. Now we give a name to the unit joules per second. 1 joule per second is called 1 watt. By the way, don't confuse this W here with this W here. This W here stands for the work done by the force F, whereas this W here is shorthand for power, the unit of power, which is the watt. So, what does this mean? It means that each second the work done by force F on this object is 200 joules. On average it is 200 joules. It depends on how the object is moving from here to here actually. If the object is speeding up, then the work done each second could change. If the object is moving with a constant speed from here to here, then the work done by force F each second will be exactly 200 joules. If the object's speed is changing, then the work done during those seconds when the object is moving fast will be greater than the work done by the force when the object is moving more slowly. Because when the object is moving more quickly, it's covering greater distance. So if it moves from here to here, say in 1 second, the work done by the force involves multiplying the force of 100 newtons by the distance travelled. But that distance covered in 1 second depends on how quickly the object is moving. The faster it's moving, the greater distance the object will move. And the greater the distance, the greater the work done by the force. So the greater the distance covered by an object in 1 second, the greater the work done by F on the object during that 1 second. So that's why this 200 joules per second is just an average. As opposed to average power, we have the idea of instantaneous power. This is the power of a force on an object at an instant. So the average power involves dividing the work done by the time taken for the work to be done. It's a similar idea to average speed. It's distance travelled divided by the time taken. But if we wanted instantaneous speed, the time taken needs to be made vanishingly small. Okay, so the time taken becomes dt. That's if we want instantaneous speed. We're looking for instantaneous power here, so instead of the change in the distance, we consider the change in the work done, dw. So this is the power of a force F on an object at an instant, and we can see it's the derivative of the work done with respect to time. So we can replace w with F times x. Now F is a constant in all the problems that we do. So we can take f outside of this derivative. If we differentiate a constant multiple of a variable with respect to time, we can just take the constant out. F is just a fixed number. Okay, it's the magnitude of the component of the force in the direction of motion. But x is something that will vary with time. X is actually the position of the object at a particular time. And notice now that we get f times dx dt, but dx dt is the speed of the object at a particular instant. It's the instantaneous speed of the object. And that's written v. So by instantaneous power, what we mean is the work done by a force in moving an object a distance dx. That's an infinitesimally small distance. Okay, so multiplying the component of the force in the direction of dx will give us the work done by the force on the object while the object moves a distance dx. And if we divide that by the time taken, which is some infinitesimal quantity dt, we have the power of the force on the object over the distance dx. That's the instantaneous power. Let's take an example. A train of weight 100 kilonewtons, that is 100,000 newtons, moves up a hill of incline 1 in 50. The resistance to motion is 20 kilonewtons, and the maximum power output of the engine is 440 kilowatts. Find the maximum uniform speed of the train. So we are assuming here that the train is moving with uniform speed up this incline. Now we know from Newton's first law that if an object is moving with constant velocity, then the resultant force on the object is 0. Now an incline of 1 in 50 means that the sine of this angle A is 1 over 50. So for every 50 meters we go along the track, we have gone up a distance of 1 meter. Since we said already that the resultant force on this is 0 because we want the train to move at maximum uniform constant speed, that is up the incline, it means that if we take the components of all the forces in a particular direction, let's say along the incline, and sum them, we'll get 0. Okay, that will enable us to find the force exerted on the train by the engine. I'm calling that force T. We could call this force the tractive force. Okay, so the engine exerts a force on the train. Right, let's take directions up the incline as being positive. Let's get the component of the weight vector along the incline. Well, you can see it's going to be pointing in the negative direction, and the same is true of this resistive force. So we don't have to worry about the components perpendicular to the incline. They'll cancel out. So what do we get? I'll just say we're getting the forces along the incline, I and C for incline. We get plus T, because it's pointing in the positive direction, minus 20,000, minus this component here. Well, we've seen before that this angle here is the same as this angle here. To get this component of the weight force, we multiply the magnitude of the weight, which is 100,000, by the sine of angle A. So that's 100,000 times 1 over 50. That's 2,000. So now we have the force on the train due to the engine. Its magnitude is 22,000 newtons. Now we are given the instantaneous power of T on the train. That's 440 kilowatts, which is 440,000 watts. We want our units in watts. We saw that the instantaneous power of a force acting on the object is the force, which is T, this is the one we're interested in, times the speed at an instant. Now we want this speed to be uniform or constant. So it's just a matter of solving this equation for the speed. Okay, let's just review what this means. Obviously, it means that each second the train covers a distance of 20 meters. Okay, the speed is uniform, so in, say, half a second, the train will cover 10 meters, and so on. We can consider the work done by T in 1 second. Okay, so we know that that's equal to t multiplied by the distance travelled by the train in 1 second. We called x in the previous video, but you know, we just multiply 22,000 newtons by the distance travelled by the train in 1 second, which is 20 meters. You see, I'm just putting everything together now. If we multiply these out, we get 440,000 Newton meters, which is 440,000 joules. Now this is the work done in 1 second, and that's the definition of power. If the force T does 440,000 joules of work on the train in 1 second, then we say the power is 440,000 watts.